Welcome to a second video on blade vibrations, a video where I would like to show you two methods to get bounds for the natural frequencies, not only for these blades, but for general applications in continuum vibrations. The first one is the Rayleigh quotient, and it's based on an energy consideration. The second method is called Dunkerley's method, and it's based on, I would say, a lumped mass modeling, a modeling like a vibration chain that you saw in machine dynamics for torsional vibrations of drivetrains, but a typical vibration chain modeling procedure. Let's start with the Rayleigh quotient. So let me remind that especially for our problem, if the bending stiffness is non-constant or mu is non-constant, we just get approximate solutions only, and therefore it would be nice to have a method at hand that allows us to compute the natural frequencies, especially the first natural frequencies, and to bound that natural frequency. So the starting point, as I said, it's energy balance based. So the starting point will be the energy balance between two states at time t and at time t equal 0, for example, or some other time. That energy balance is here formulated with the kinetic and the potential energy, as there are no dissipative forces included in our modeling procedure. For the kinetic energy, we have half the volume integral on the mass density ρ times the velocity field squared dv. V would be a vector quantity. Here in our case, of course, it's just a scalar quantity because we consider just one displacement. And well, the first thing is that as we are dealing with the rod theory, so with a one-dimensional theory, we integrate out the other two directions, so the other two dimensions here. That is, we would obtain a single integral over just the direction xi, ranging from 0 to 1 because we normalized xi. Usually we would have a dx here, if x corresponds then to xi, or xi corresponds to x divided by L, and therefore the change of variables leads to an L d xi for the differential, so therefore the L appears here. We integrate out the other two directions, so y and z directions, as everything is constant with respect to these directions, because we are considering just a one-dimensional theory here. We would obtain the cross-section area A, and the product of ρ times cross-section area A is then this constant mu here. So we get mu omega squared. Well, you would say, where is the derivative with respect to time? But already Bernoulli separation has been used here, omega squared theta dot squared, and that dot is the time derivative we need for the velocity here. Omega dot squared theta dot squared, and theta dot is independent of xi, and therefore it appears outside of that integral. This would be the kinetic energy. What can be said about the potential energy? Well, the potential energy here for, again, a rod is the normal stress times the normal strain, half the normal stress times the normal strain, and also integrated over the whole volume. Now you reduce everything to strains first by applying Hooke's law for rod theory, so replacing sigma by the Young's modulus E and epsilon 1,1, so you get E epsilon 1,1 squared. You have to integrate over the whole volume of that element. You insert for E11 minus Wxx z, so the relationship for beams between strains and the second derivatives of the displacements, so a linear relationship when it comes to the change in z. And then you also integrate out the result, so you would have plus, because it's squared, plus wxx squared z squared, the integral over the volume. You take the integral over the area, so of the two other coordinates, which would be y and z, and as you integrate z squared dz, you have to introduce the second moment of area here. So when you integrate just with respect to x, from 0 to L with respect to x, you have to introduce the second moment of area, I here, so we recover the bending stiffness E times I. We normalize that integral by, well, substituting dxi or xi instead of x. This leads to a leading factor of 1 divided by 2L in third power. You will wonder why. Here we had a factor of L and now we have 1 divided by L in fourth power. Well, because we have the second derivative that we have to transform. And this leads to 1 divided by L squared. And as we have to square the second derivative, we have 1 divided by L in fourth power. The transformation of the differential then yields L divided by L in fourth power, leading to 1 divided by L cubed. And finally, well, we do not have only the uppercase W in second derivative, but we also have to take theta squared into account. That is, we replace the second derivative by the second derivative of capital W and theta. Okay, so this would be the result. And now we would have our energy balance. So the energy balance, by inserting this expression for the potential energy and my expression for the kinetic energy, would read as follows. Half L integral from 0 to 1 mu W squared psi d psi theta dot squared plus 1 divided by 2L in the third power, and the integral from 0 to 1 E times I W double prime squared d psi theta squared. We know that we would yield the maximum of the kinetic energy for theta dot max, and that appears if V is minimum, and minimum, as it's a positive quantity, is equal to 0, and we would obtain the maximum of the potential energy for theta max, and that would happen at T equal to 0, kinetic energy is equal to 0, which would be the minimum of the kinetic energy. It's like for the pendulum. You have the turning points where you have a maximum of the potential energy, and then you have the case that the potential energy is 0, and there you would have maximum of kinetic energy. And there's one relationship that relates the maximum of the kinetic energy, so theta dot max, to theta, as these are just the derivatives of each other. We would find omega theta max, knowing that differential equation for theta. Yeah? So this is the point where omega, the natural frequency we are looking for, appears in that equation. And now we can introduce these relationships into the equation. So we equate on the one hand T max, which must then be equal to V max. So we equate two states. And for the state T max, we insert for theta dot max omega squared of theta dot squared max. We insert omega squared theta max squared. Then we can divide both sides by theta max squared and solve for omega squared, and we obtain the following expression. We obtain the term, the integral 0,1 EI W in the second derivative squared d psi. So I would say the rest of the potential energy, the numerator stems from the potential energy. The half here, the two half go away. You divide by 1.5, and you get L in fourth power in the denominator, and the rest in the denominator stems from the kinetic energy. It's the integral 0 to 1 mu W squared d psi. And that quantity is termed the Rayleigh quotient. Basically, what the Rayleigh quotient in this way tells you is once you have the mode shape, you can get the natural frequency by, well, dividing these two integrals, the first one stemming from the potential energy, the second one stemming from the kinetic energy. However, you do not have the mode shape, because once you have the mode shape, you have computed before, I guess, the natural frequency. So when you have the mode shape, there is no need, I would say, to evaluate the Rayleigh quotient to determine the natural frequency, because you did this step before computing the mode shape. However, what happens if you do not know the mode shape? Then, well, you can perhaps use an approximation, polynomial or whatsoever, for that mode shape, and you would compute an approximate solution for that omega. Now, what can be said about that approximation of that omega related, of course, to the true omega? No? So, the idea is, let's compute the approximate solution with the Rayleigh quotient. We just have an approximation of that mode shape. We represent that mode shape in the basis of the correct modes. Although we do not know it, just for mathematical purposes, we represent it in that basis, so that can be seen as like a vector basis or basis of a vector space. And you have an expansion in that vector space. Now our vector space is infinite dimensional because it's a function space, like the Fourier spaces for cosine and sine harmonic functions. And we just know that function or W tilde, that's our choice. We do not know that representation, but for the moment we do the computations with that representation just to see how to relate the approximate solution computed by the Rayleigh quotient for the natural frequency to the true natural frequency. And what we will see is that our approximate natural frequency, that's what I can prove, that our natural frequency is that the approximate natural frequency is always larger than the natural frequency computed, the true natural frequency computed with the two corresponding mode shapes. So let me prove this, and therefore I need this representation here. So I will make a further assumption regarding our approximate solution for the mode shape. The approximate solution has to satisfy the geometric boundary conditions. Let's insert this into the Rayleigh quotient here, R sub W, R of W. Then we have AI squared 0, 1 EI WI double prime squared psi d psi, and L in fourth power I equal 1 to infinity A sub I squared 0, 1 mu WI squared psi d psi. Let's study this modified Rayleigh quotient, so the Rayleigh quotient not for W, but for W tilde, so there must be a tilde here on the W, for W tilde in more detail. So let's add and subtract to this an omega 1 squared in order to show the relationship with respect to omega 1 squared. So what I want to prove is that this term here is always positive, so that my approximation R of W tilde of omega 1 squared is always larger than this omega 1 squared, and happens to be omega 1 squared if I select the correct mode shape. So if all the coefficients A sub I are 0 except for the first one, A1, which should then be equal to 1. So first of all, let's see that I added omega 1 squared, but that I also subtracted omega 1 squared. Well, you can see that this term here corresponds to the denominator, L in fourth power, the sum running from I equal to 1 to infinity AI squared 0, 1 mu WI squared psi d psi. Now I can switch here. In the first integral, I can switch to also a representation including mu wi squared psi d psi. So I can switch from, let's say, potential to kinetic energy. Yeah? Well, I can then see that I have to take the difference of the omega i's, because if I switch here to kinetic energy, the omega I squared will appear, but here there is only omega 1 squared minus omega 1 squared ai squared, and then the integral from 0 to 1 mu wi squared psi d psi. And I divide by the sum running from I equal 1 to infinity ai squared, integral from 0 to 1 mu wi squared psi d psi. So that you can switch from potential to kinetic energy just is done with the same argument as before, the energy conservation here. Okay, and now if you look at that expression, then you clearly see that, well, what I promised to you is true. That expression is always larger than omega 1 squared. It's positive, not larger than omega 1 squared. That expression here is positive, so the whole expression is larger than omega 1 squared, because the natural frequencies are ordered. And omega 1 is the lowest natural frequencies. The omega i's are higher natural frequencies. Therefore, this factor is positive. But all the other factors must be positive, because ai is squared here and there, and wi is also squared, and mu is a positive factor. So the whole thing must be positive. It is exactly equal to 0 if, again, as I said, all the coefficients ai are 0 except for the first one. And for the first term, I would then obtain omega 1 squared minus omega 1 squared. So the numerator would be completely 0, and therefore the whole expression has to vanish. So let me summarize the results. We have seen that w tilde is larger than omega 1, and that for the reason that my natural frequencies are ordered, and therefore this coefficient is positive, and the rest is positive as well. Now what to do for higher mode shapes? So if you want to approximate not omega 1 squared, but some other, let's say omega 3 or omega 4 or some higher mode, then you have to assure that the coefficients a sub I for these lower mode shapes are 0. So your approximation must not only satisfy the geometric boundary conditions. By the way, if it would not satisfy the geometric boundary conditions, you were not able to derive a representations on the function space of the mode shapes, because all the mode shapes, by definition, have to satisfy the geometric boundary conditions. So it's not by superposition of functions that satisfy the geometric boundary conditions. It wouldn't be possible to construct something that violates the geometric boundary conditions. So not only that excursion, not only you have to satisfy with your approximations the geometric boundary conditions, but you have also to make certain that they are, in the sense of a scalar product running from 0 to 1 d psi, are orthogonal to the lower mode shapes to assure that these coefficients a sub I vanish for the lower modes, so for I running from 1 to n minus 1, if you want to determine the natural eigenfrequency omega sub n. Then the same reasoning would hold. Of course, you would have an omega n squared. You would see here coefficients that are negative, if this is omega n for values I less than n, but they are killed by coefficients a sub I, the projections on the modes that are equal to 0 due to orthogonality. So in this way, you can use that Rayleigh quotient also for higher order mode. So now let's see how this works. So Let's take a, well, homogeneous cantilever beam. So a cantilever beam as for our stator blade, and homogeneous so that we can compare the approximate solution with the exact solution. A first guess for the first natural, or for the first mode shape, if you look at that function, where you have to satisfy the natural, the geometric boundary conditions, and then you remember it was a function that has no zero crossing, so we take xi squared between 0 and 1. The geometric boundary conditions are clearly satisfied. However, we violate here one of the boundary conditions, dynamic boundary conditions at the free end, namely the second derivative is clearly non-zero, it's 2. Yeah? Okay, how good is this? We get omega 1 squared is always less than EI ln fourth power, the integral from 0 to 1 of the second derivative, which happens to be 2, squared, so 4, divided by mu, 0 to 1, xi in fourth power d xi. If you make the computations, you see first, you get the physical properties right. The dependence on the bending stiffness, on mu, and on L in fourth power is the famous factor we saw in our partial differential equation in the last video, in our differential equation that describes the bending vibrations of a beam. The factor is a 20. So if you compute then omega 1, you take the square root of that 20 and the square root of that factor, leading to 4.472. We computed lambda, or gave lambda 1 as being 1.875 on 3 digits, on the precision of 3 digits. And if we do the same with that value of omega, so of our approximation, we have to take again the square root of the leading factor, 4.472. That yields 2.115. Can we do better? I mean, that's quite okay, I would say, for an engineer, but, well, you see, I'm not really satisfied. We can do better. Let's take a second guess. A guess that satisfies now all the boundary conditions, so ideally suited for a projection on the mode shapes, therefore. So as you can see, I added just, or I enlarged the space, the polynomial space used here for approximation to third and fourth power, such that the boundary conditions are then satisfied. Well, you repeat the computations. I believe that you are able to solve the integrals here and also to take the derivative of that expression. It just involves the polynomial. So I would just state the result. It's 1.879. Well, suppose, well, of course you see it's perfect. It's really, even for an engineer, it's, well, no doubt that this result is sufficient for engineering precision. Yeah? But suppose you did not know the value of 1.875 and you just repeat the computations with 2 candidates, like here and there. You're not sure, maybe you exaggerated here, maybe you went in the wrong direction, and you get the 2 results. Can you tell, just from looking at the results, which one is the better one and which guess is the better one? Yes, you can, because you know that you always get something that is larger than omega 1 squared. So if you get 2 results, then you take always the smallest one, because you know that both results must be larger than omega 1 squared. So you get upper bounds for omega 1 squared, and obviously the second bound is narrower than the first one. So therefore, this is the better result, without looking at the 1.875, without looking at whether you did everything correct here or not. Just if you would write down these 2 guesses or approximations, and you do the computations, and you end up with a value that is smaller, and maybe you want to add some other terms to make it even smaller, then you would know the narrowest bound, the smallest value, is the best one, and therefore also the mode shape must be the best one, of course. Okay, so we have determined an upper bound. What would be nice is to have a lower bound, because then you know for sure that in between the lower and the upper bound sits your natural frequency. Now let's determine a lower bound for the first natural frequency. So therefore we need a completely different approach. So basically consideration of the energy conservation is already finished, has led to one result. There's no hope to get a lower bound following the same way we did for obtaining an upper bound. Yeah? So, and that completely different approach is on a lumped mass modeling and on a vibration chain. And well, this is shown starting from the next slide, and it is called Dankeley's method. So as I said, the starting point is a vibration chain with n masses. So we split our bar into n segments, well, of equal length. The length is then L divided by n, and well, the mass is then, well, if mu happens to be different, so non-homogeneous beam, mu of the center of that segment times L divided by n. So just an approximation, well, where you take the mass approximately constant in each segment. Well, we need equations of motion for that vibration chain, and they are obtained on the one hand from a force balance, where we have the inertial force and some other force F sub I acting, well, on that segment. The force F sub I is related to the displacement by influence coefficients, so in the sense of Maxwell. So we have Wi is equal to J equal 1 to n alpha ij fj. And this will be, and it's interesting, this will be the starting point for the equations of motion, because this is already the restoring force here. Now, if you insert for F sub j from your force balance, say, could also say the inertial force, you would arrive at an equation of motion. You did not consider, well, stiffness coefficients, but well, flexibility coefficients, coefficients that are multiplied with the inertial term and not with the restoring force terms or with the displacements. So we insert the first equation, or I could say we insert the inertial forces into the second equation to yield omega Wi is then plus j equal 1 to n alpha ij mj Wij double dot is equal to 0. So we put this term on the left-hand side with a negative sign, but F sub I is also a negative sign. The inertial forces appear in the sense of D'Alembert with a negative sign. And this would now be the equation that governs our vibration chain. Now for that vibration chain, we also have the time behavior, well, as before for the beam, as a harmonic behavior. So we know that the second order time derivative of Wi, so for each displacement of each segment of the segment center, we get minus omega squared Wi, a harmonic time behavior. We insert this relationship here and we get Wa divided by omega squared. So I divided by omega squared, the sign has to be changed here, alpha ig mj Wj, and the sum runs from 1 to n. This is an equation for the amplitudes Wi and Wj. So it's a coupled set of equations, and as you can see, it has been at the very beginning an ordinary differential equation. But due to the setting, we now leave the ordinary differential equations and we have an algebraic equation for Wi. And that algebraic equation can be written in matrix form. That's done on the next slide. And in that matrix form, you will find everywhere the influence coefficients, so the matrix of influence coefficients running from alpha 1, 1, m sub 1, first row to alpha n1, m sub 1, and in the nth row, first column, and in the nth column from alpha n1, mn to alpha nn, mn. And on the diagonal, you have the terms, well, the restoring force terms, I could call them -1 divided by omega squared with the appropriate displacement. So therefore, they appear here on the diagonal. Well, you want to have non-trivial solution. This would be the coefficient matrix of your linear algebraic problem. You want to have non-trivial solutions for these amplitudes, for these displacements omega I. Otherwise, they would be all zero and there would be no vibration. The system would be at rest, which is not an acceptable solution for our situation. So, well, you would get the eigenvalues from solving that eigenvalue problem here, for solving for omega squared, 1 divided by omega squared, for example, which would be then, the solutions would be omega 1 squared until omega n squared, and would be n natural frequencies. However, there is much more to tell about eigenvalues of a matrix, of that matrix here. So we need the n roots, which are 1 divided by omega I squared, and we know that the trace of that matrix is equal to the sum of the eigenvalues. Now the eigenvalues are written here by that omega 1 divided by omega squared. That appears perhaps a little bit strange. You would write a lambda there, yeah? But suppose there would be a lambda, you would take the sum of all these lambda values or different eigenvalues. So the sum of lambda 1 to lambda n, sum of the eigenvalues, and you know it is the same as the trace of that matrix, which is alpha 1, 1, m1 to alpha nm, mn. So this is a result coming from linear algebra. Well, and this result allows you now to solve or to establish a lower bound for the natural frequencies, because now the natural frequencies, they appear in the denominator. Well, they appear all as positive quantities. Well, they are positive, of course, the natural frequencies, and they appear even in the square. You know that they are ordered. We ordered them starting with the smallest one, leading to the largest contribution here. And then we have higher natural frequencies, and the higher the natural frequency, the lower the contribution here. So if we replace that sum just by the first term, of course, we leave out a lot, namely the other n-1 terms. We know that everything that we leave out is positive, so that we can replace the left-hand side by 1 divided by omega 1 squared, and we are sure we get 1 divided by omega 1 squared is lower than this sum. That would be the relationship, from which we get that omega 1 squared is larger, always larger than the sum of the trace of that matrix here, well, to the power of -1. Yeah? Because you invert both sides of that inequality, and of course you don't forget to change the sign of the inequality then. So we get omega 1 squared is larger than the sum from 1 to n alpha I mi. So the trace 1 divided by the trace of that matrix. And now we generalize this result to the case that we take smaller and smaller segments for the discretization of our beam. And then this sum here, well, will be a Riemannian sum, where it converges for the case that n, the number of sequence, tends to infinity, that this converges then to an integral running from 0 to L. Alpha x m sub I is then replaced by the linear mass density rho times a mu x dx. And don't forget to take this to the power of -1, so it's in the denominator here. Okay, so all you need is this, well, would say at the beginning, these were the influence coefficients, and now it's a function of influence coefficients. Now, let's see how this works and how to determine this function alpha x. And again, the exercise is the homogeneous cantilever beam. So now I would like to establish a lower bound, and together with the upper bound for the natural frequency, we then see how large that interval will be in which our value 1.875 is placed. So first of all, how do I obtain that function alpha of x? Well, because once you know that function alpha of x, and for our case, homogeneous cantilever beam, mu is a constant, you just have to solve that integral then. So suppose you study the following load case. You have a force F on your cantilever beam sitting at a position x hat. You compute the bending line, so the deflection line, either from looking at tables, textbooks, where you find these deflection lines, or by doing the computations at hand, solving the problem of engineering mechanics 2, I think, strength of material or strength of structures, here structure strength, the classical problem of computing a bending line for a force at position x hat, satisfying the boundary conditions for the cantilever beam, the geometric boundary conditions at x equals 0, and the free end boundary conditions at x equal L here. You would get this solution, where you have the force F divided by 2EI x hat x squared minus x cubed divided by 3. How do you get then alpha x? Do you remember the alpha x? Well, you can see it here. They are obtained from alpha II. So from the influence coefficients, where I put a force at position, let's say x hat, and I compute the response at the same position x hat. That tells you alpha II. The first one is where, the second one is where you put the force, and the first one is where you want to obtain the response. These are the coefficients alpha ij, and here, as you take the trace of that matrix, you just have to consider coefficients alpha sub ii. So therefore, we have to identify x hat as x, so either we have to put on any x here a hat, but if you are lazy, then you would drop the hat of that x here, leading to x in third power minus x in third power divided by 3. So clearly this is 2 divided by 3, x in third power. So your alpha x is then, as we have another 2 here, f divided by 3 ei x cubed. This one. And that's a function you have to integrate. And then you get your result here, your Dunkerley bound. So this is then the easy part. So you have 1 divided by omega 1 squared, which is then the integral from 0 to L, always larger than the integral of 0 to L of alpha x, plus alpha x being x cubed divided by 3. So clearly then you get mu L in fourth power 12 divided by EI. And then you switch the denominator on both sides, so you get omega 1 squared is larger than 12 EI divided by mu L in fourth power. Now you have to take omega, so the square root, especially the square root of the 12. You see from the square root, or you already see from the physical quantities that you get the physical quantities right. So the dependence on the parameters is completely correct. You get a square root of 12, and you have to take another square root to arrive at a bound for lambda 1. So the 12 to the power of 1 divided by 4, and this is 1.861. Perfect. You have a lower bound 1.861. You have the correct value to 3 digits, 1.875, and you had an upper bound, if I remember well, it was 1.878. No, maybe a little bit larger, I don't know, but this would be a really narrow interval. So an engineer is really, really happy for this. This is an excellent estimate, And it is based solely on influence coefficients, so solely on statics, I would say, on that computation here, the beam deflection, and nothing else. So statics already can help you to establish such a lower bound for the natural frequency. Yeah, and that's all I would like to show you in this video. So now you have seen two bounds. The first one based on an energy principle, it's the Rayleigh quotient that allows you not only to compute an upper bound for the first natural frequency, but after orthogonalization also of higher natural frequencies. It's based on approximations of the mode shapes also. The second one is totally based on influence coefficients, therefore on statics, and allows you already to compute a lower bound of the first, but only the first, and this is the disadvantage here, natural frequency. Well, this is the end of that video, and in the next video we will then move to the rotors and to turbine blades mounted on rotors and include or study the influence of the centrifugal force and the influence, of course, of the rotational velocity of that rotor on the bending vibrations. Therefore, I would like to thank you for your attention, and I hope I see you in the next video. Thank you.